Chapter 1 of Science and Hypothesis. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Ashwin Jain. Science and Hypothesis by Henry Poincare. Chapter 1 on the nature of mathematical reasoning. The very possibility of mathematical science seems an insoluble contradiction. If the science is only deductive in appearance, from whence is derived that perfect rigor which is challenged by none? If, on the contrary, all the propositions which it enunciates may be derived in order by the rules of formal logic, how is it that mathematics is not reduced to a gigantic tautology? The syllogism can teach us nothing essentially new. And if everything must spring from the principle of identity, then everything should be capable of being reduced to that principle. Are we then to admit that the enunciations of all theorems with which so many volumes are filled are only indirect ways of saying that A is A? No doubt we may refer back to axioms which are at the source of all these reasonings. If it is felt that they cannot be reduced to the principle of contradiction, if we decline to see them in any more than experimental facts which have no part or lot in mathematical necessity, there is still one resource left to us. We may class them among a priori synthetic views, but this is no solution to the difficulty. It is merely giving it a name. And even if the nature of the synthetic views had no longer for us any mystery, the contradiction would not have disappeared. It would have only been shrugged. Syllogistic reasoning remains incapable of adding anything to the data that are given it. The data are reduced to axioms, and this is all we should find in the conclusions. No theorem can be new unless a new axiom intervenes in its demonstration. Reasoning can only give us immediately evident truths borrowed from direct intuition. It would only be an intermediary parasite. Should we not therefore have reason for asking if the syllogistic apparatus serves to disguise what we have borrowed? The contradiction will strike us the more if we open any book on mathematics. On every page the author announces his intention of generalizing some proposition already known. Does the mathematical method proceed from the particular to the general? And if so, how can it be called deductive? Finally, if the science of number were merely analytical, or could be analytically derived from a few synthetic intuitions, it seems that a sufficiently powerful mind could with a single glance perceive all its truths. Nay, one might even hope that some day a language will be invented simple enough for these truths to be made evident to any person of ordinary intelligence. Even if these consequences are challenged, it must be granted that the mathematical reason has of itself a kind of creative virtue, and is therefore to be distinguished from the syllogism. The difference must be profound. We shall not, for instance, find the key to the mystery in the frequent use of the rule by which the same uniform operation applied to two equal numbers will give identical results. All these modes of reasoning, whether or not reducible to the syllogism properly so called, retain the analytical character, and ipso facto lose their power. 2. The argument is an old one. Let us see how Leibniz tried to show that 2 and 2 make 4. I assume the number 1 to be defined and also the operation x plus 1. That is, the adding of unity to a given number x. These definitions, whatever they may be, do not enter into the subsequent reasoning. I next define the numbers 2, 3, 4 by the equalities, equality 1, 1 plus 1 equals to 2, equality 2. 2 plus 1 equals to 3, equality 3. 3 plus 1 equals to 4, and in number 4. The same way I define the operation x plus 2 by the relation 4, x plus 2 equals to x plus 1 plus 1. Given this, we have 2 plus 2 equals to 2 plus 1 plus 1. 2 plus 1 plus 1 equals to 3 plus 1. 3 plus 1 equals to 4. Whence 2 plus 2 equals to 4. QED. It cannot be denied that this reasoning is purely analytical. But if we ask a mathematician, he will reply, "This is not a demonstration properly so called, it is a verification." We have confined ourselves to bringing together one or other of two purely conventional definitions, and we have verified their identity. Nothing new has been learned. Verification differs from proof precisely because it is analytical, and because it leads to nothing. It leads to nothing because the conclusion is nothing but the premises translated into another language. A real proof, on the other hand, is fruitful because the conclusion is in a sense more general than the premises. The equality 2 plus 2 equals to 4 can be verified because it is particular. Each individual enunciation in mathematics may be always verified in the same way. But if mathematics could be reduced to a series of such verifications, it would not be a science. A chess player, for instance, does not create a science by winning a piece. There is no science but the science of the general. It may even be said that the object of exact science is to dispense with these direct verifications. 3. Let us now see the geometer at work and try to surprise some of his methods. The task is not without difficulty. It is not enough to open a book at random and analyze any proof which we may come across. First of all, geometry must be excluded, or the question becomes complicated by difficult problems relating to the role of the postulates, the nature and origin of the idea of space. For analogous reasons, we cannot avail ourselves of the infinitesimal calculus. We must seek mathematical thought where it has been remained pure, that is, in arithmetic. But we still have to choose. In the higher parts of the theory of numbers, the primitive mathematical ideas have already undergone so profound an elaboration that it becomes difficult to analyze them. It is therefore at the beginning of arithmetic that we must expect to find the explanation we seek, but it happens that it precisely in the proofs of the most elementary theorems that the authors of classic treatises have displayed the least precision and rigor. We may not impute this to them as a crime. They have obeyed a necessity. Beginners are not prepared for real mathematical rigor. They would see in it nothing but empty, tedious subtleties. It would be waste of time to try to make them more exciting. They have to pass rapidly and without stopping over the road, which was trodden slowly by the founders of the science. Why is so long a preparation necessary to habituate oneself to this perfect rigor, which it would seem should naturally be imposed on all minds? This is a logical and psychological problem which is well worthy of study. But we shall not dwell on it. It is foreign to our subject. All I wish to insist on is that we shall fail in our purpose unless we reconstruct the proofs of the elementary theorems and give them not the rough form in which they are left so as not to weary the beginner, but the form which will satisfy the skilled geometer. Definition of addition. I assume that the operation x plus 1 has been defined. It consists in adding the number 1 to a given number x. Whatever may be said of this definition,